share the whiteboard. Okay, so let's review a little bit of note things from the last time that we were together. Okay, good. Looks like everybody's up and everything's good. It's always a game to make sure everything is turned on. Okay, so that pen will not help me. Let's refresh the two main kinds of energy. We have potential energy, and the one we're going to work with is gravitational potential energy. So some people just call it GPE. You can also see it written. I don't know why I'm putting what am I doing? I need parentheses around that. Some people will also write this as potential energy in physics is a capital U, potential gravitational, so potential energy that's gravitational. So you'll see all of these phrases, they mean the same thing. And just to refresh, this is the energy stored in the gravitational field. So this is the energy stored in the gravitational field. So let's say we had, I can do better than that. Let's say we're trucking along and our little cart is rolling with us. Here we are, walking forward and pulling our little cart behind us. When we talk about gravitational potential energy, just to refresh, you get to pick what you call the zero height. So you get to pick where we're going to measure height from. All right? Most of the time, what we want to do is put the height equals 0 at the lowest point. Is a good choice. The reason we want to do that is because that way every place I go is a positive number, because every place I go would be either the same height as 0 or I will be a positive number. So when we talk about the potential energy, you have more energy when you're further from the surface of the Earth. So here I would have some potential energy, and over here at the top of this hill, I would have more potential energy. So the further I get from my ground, the more potential energy I have. If I'm on the ground, I have no potential energy. Okay? Now, some people like to put whatever they start with as their 0, and that's okay too. But let me give you a caution here, because let's say, and it's way too cold to do this now, a couple of weeks ago would have been fine, but let's imagine for a second that here's the beach, and we're out and there's the water, and it's a lovely day, and we want to go play in the water. So when you call ground height 0, if I make ground height of the top of the water 0, then what happens when I'm down here doggy paddling for my life? Well, now my height needs to be a negative number for height. And that's kind of upsetting. So if I was doing something where I was at the beach and I'm going to scuba dive, or I'm in a submarine and I'm going below water level, I might still want to put the lowest position as my 0, and that'll make all my heights be positive every time. That way I don't have to worry about signs, like plus and minus signs. Okay? So let's show you the formula. Actually, I'm going to clear all this. Let's show you the formula for this. So potential gravitational energy is mass times gravity times height. So for us, that is m. This number is 10 meters per second squared. And this is your height. M is your mass. Okay, so let's do a roller coaster problem. Let's make this 40 meters. Let's make this 30 meters, 10 meters. And I'll call this A, B, C, and D. All right. So what is the gravitational potential energy at A? Well, how big do we want to make our car? A 4-person car, 6-person car, 4-person? Okay. So we're going to make this 300 kilograms. That's how big our roller coaster cart's going to be with 4 people in it. So we got 4 people in it, plus the cart, 300 kilograms, about 600 pounds altogether. That'd be about right. So what is our gravitational potential energy? Well, it's our mass times gravity's acceleration, which is 10. And where are we going to put our 0 height? Where would be the good place to put our 0 height? Well, probably here at the bottom of the roller coaster, right? Since you told me the height above ground in each of these cases, I'm going to make this my height equals 0. So point A would be 40 meters above ground. Everybody okay with that? You get to pick where you put the 0 height. I put it at ground level for the bottom of the roller coaster, the lowest point. So then our potential energy would be 300 times 10 is not 4 something.
120,000.
Yes. Thank you, Michael. You said 120,000?
Yes, ma'am.
Okay. So this comes out to be 120,000, and the unit is joules. So let me show you where that comes from. We have a kilogram. We have a meter and another meter, so we have meters squared. And on the bottom, we have seconds squared. So because physicists get tired of writing just like you do, we don't want to have to write kilogram meter squared over second squared every time we do this. So we made a unit and we called it the joule. So a joule is a kilogram meter squared per second squared. Both of those things mean the same thing. But since we're basically lazy, we use joules.
Excuse me, if acceleration is measured in seconds per second, so like
Yes.
kilogram meters per second is like force. Why is second squared if it's second per second, like second over second?
Oh, okay. Good question. Let me come over here to answer that. So acceleration is a change in velocity over a change in time. So velocity change would be meters per second. And then the change in time would be per another second. So Michael is asking how this turns into meters per second squared. So let me actually move to another slide for this. Let's go over here. So if I have meters per second over seconds is acceleration. If you'll recall, when you do division with fractions, you have to multiply by the reciprocal of the second fraction. So we change this to times, and we flip this fraction over. So then you get meters times 1 on top is meters, and seconds times seconds on the bottom is seconds squared. So meters per second is the same thing as meters per second squared.
Okay, I understand. Yeah.
Is that better?
Yes, ma'am.
Okay. Now for most of us, what we do is we do this. Okay. I'm going to go back to the other page real quick. What if I wanted to know the potential energy at point C? What does point C look like it is? Where does it look like it's located?
At the 15-meter mark.
Okay, Michael's going to say he thinks it's at the 15-meter mark. Where do you think C is? If B is at 30, where is C? It looks about like halfway, yeah? Be 15 meters. So do we have more potential energy at B or more potential energy at C? Which one would have more energy stored in the gravitational field?
B
B or C? Yeah. How do we decide? Potential energy depends on how far you are off the ground. So who is further from the ground? B. Since B is further from the ground, it will have more potential energy. Then C, then D. So as you move through this roller coaster, you get more potential when you go up and you get less potential when you go down. Okay? So let's find that, the potential energy at C. So potential energy at C, where the height equals 15 meters. Well, potential energy is mass times gravity times height. My mass was 300. My gravity was 10. And my height is 15. So this becomes 3,000 times 15. And that is 45,000 joules. So my gravitational energy is 45,000 joules. How are we doing out there? People out there in the back? People in here in the back? Doing okay? I'm going to wait because I know some people are still writing. Yeah, go ahead. You got it? Thanks, James. So I'm going to go back to the worksheet now. We're going to work a couple of these together. So let's flip back over to the worksheet. And the first question I ask here is kinetic energy, potential energy, or both? Kinetic energy, potential energy, or both? So what does kinetic energy depend on? What's kinetic energy? The energy of what? Moving. It's the motion energy. So if I'm at rest, Can I have kinetic energy? Can't have kinetic energy. So number 1 says, if an object is at rest, it certainly does not possess this form of energy. So if an object is rest, it would have potential energy. It would not have kinetic. Nope, the answer here is kinetic. You might have potential, we don't know. So it does not have kinetic energy if it's not moving. So number 1 is kinetic energy, because it doesn't have it. It asks what you do not have, not what you do. You okay now? This is KE. Which kind of energy depends on mass and height? Height off the ground. That one depends on, potential energy depends on mass and height. So that's what we were just doing. When we were just doing our whiteboard, what did potential energy depend on? Potential depends on mass and height. Okay? Let's stop that share. Let's go back to this share. Okay. All right. Let's go down here and work one of these. Let's work number 3. A young boy's glider is soaring through the air, possessing 0.80 joules of potential energy. If its speed is doubled and its height is doubled, then the new potential energy will be what? Okay, well, let's give myself a place to work here. So what happens? Potential energy is mass times gravity times height. And we know this number over here is 0.80. So what did we do in this problem? What did we change? Well, gravity doesn't change, right? Gravity's 10. Gravity's acceleration is 10 every time we see it. But we did do something to the speed. Is speed part of my equation? Speed part of the potential energy equation? No, it's not. So that part doesn't matter. But they also said, so this part doesn't do anything for me, but they said its height is doubled. So I would put a 2 height in here instead of a 1 height. I doubled it. And I didn't change the mass. So if I put a 2 in on this side, what has to happen to the other side? I have to do the same thing. So if I double the height, I double the energy. So my answer here would be, I now have twice as much energy because I'm twice as far off the Earth. I have twice as much energy because I'm twice as far off the Earth.
It said its speed was doubled too, right?
But it asked me only about the potential energy. So it is going faster, so it'll have more kinetic energy also, but they didn't ask me about kinetic.
Oh, so in other words, the acceleration wouldn't be affected?
The acceleration would be the change in speed, and we're not really worrying about that part here because it does not affect my potential energy. Potential only is related to how high off the ground you go. So since they only ask about potential, I wouldn't worry about the fact that it accelerated or it has twice as much speed. Yeah.
All right, because I was just looking at the acceleration due to gravity, and I was wondering why it wasn't doubled.
Yeah,
but
two things going. Michael, hang on for a second. No, go ahead. Kinetic energy is going to depend on the speed. So in the kinetic energy, we would have to do something with it. We're going to look at that kinetic energy here in just a second. Now, Michael, what did you say?
I was saying, I was just looking at the acceleration due to gravity, which was 10, and I was wondering why it wasn't doubled, but I get what you're saying.
Okay. Well,
Uh,
and what's true about our gravitational field? Does our gravitational field get bigger or smaller? Does
No,
gravity around Earth change?
no, it doesn't.
It doesn't until you get way out in space. So acceleration due to gravity for all our purposes is always going to be 10. It's a good question though.
All right.
Okay, so let's go down and let's do number 7. Calculate the potential energy of a 5.2 kilogram object positioned 5.8 meters above the ground. So potential is mass times gravity times height. So potential energy would be 5.2 times gravity, which is 10, times 5.8. See, that's about 25 times 10, so 250, 260, something like that. You shall check.
I'm getting 301.6.
301, okay. Well, just ballparking in my head, I wasn't sure how much the 2 decimals were affecting it. Yeah, 301.6. And our unit will be the joule. We measure energy in joules. Okay. I'll wait there to see if anybody has a question. Okay. And let me show you how to do these. Okay. Because we're fixing to talk about kinetic energy and total energy. So on these questions, number 13, you're going to tell me, does the kinetic energy go up, down, stay the same? Potential energy go up, down, stay the same. TME is total energy, total mechanical energy. And I say that on the worksheet, okay? It says that on the worksheet. So let's look at number 1. A marble begins at an elevated position on top of an inclined ruler and rolls down to the bottom. So I have a slant, I put a marble up here and I let it roll to the bottom. What happens to its kinetic energy? Does it go faster? Does it go slower? Does it go the same speed? What does the marble do as it rolls down the hill?
It increases in speed.
It's going to go faster. Just like if I drop things, they're going to go faster. So our kinetic energy will be going up. Kinetic energy goes up. Yeah, I'm on the back of that single page. Yep. Bottom part. So my kinetic energy goes up. But if I'm going downhill, my potential energy will need to go down. As I move closer to the earth, my potential energy goes down. So kinetic goes up because I'm going faster. Potential goes down because I'm getting closer to earth. So what do you think happens to the total energy? I would say they're probably equal. One gained, one lost, probably equal. Do not put question mark on any of these. No question marks. Because all of these have answers. Okay. Let's do number D. Let's do letter D. A physics student runs up a staircase at constant speed. Well, we're running at constant speed. Do we have kinetic energy? If we're running, we do. If we're moving, we do. Does our speed increase, decrease, or stay the same? We're at constant speed, so it stays the same. But we're running up a staircase. So what happens to potential energy? We're going uphill. We have more potential energy. We're further from the Earth. So now what happens to our total energy? We have a stays the same and an increases. So our energy would
increase.
Overall, it would increase. You see how those work? Okay. All right, let's do the formula for kinetic energy real quick, and then I'm going to let you loose on these two. Realize that the second packet, the longer one, has a lot of pieces to it. I'm going to talk to you about that before I stop class today. But this one is going to be due Friday. This one will be due Friday. All right, so now let's stop this share and let's go back to the whiteboard. Okay. All right, so on the whiteboard, kinetic energy, you will see it written as KE or just plain K. This is kinetic energy. You have kinetic energy if you're in motion. If the object is moving. So even though Miss Wilson is not moving around a lot, I am moving. My eyes blink, my heart beats, I breathe, sometimes better than others because of sinus congestion this time of year. And the fact that we went from 70 degrees to 20 degrees in like 2 days. Yeah, some of you have that too. But I have lots of moving parts inside my body. But if I start walking, I'm also moving. So anytime any part is moving, things that are moving always have kinetic energy. The formula for kinetic energy is 1/2 mass times velocity squared. Notice it's only the velocity that gets squared. So our formula is 1/2 m and the v is squared. Not parentheses mv, just v is being squared. So the faster you go, the more kinetic energy you have. And that energy has to go somewhere. So it goes out a lot of times as friction. Like if you're like me this morning when I drove to school, my car tires were a little bit flatter than they needed to be. They're a little bit flatter because it's really cold outside. And so the air in the tires had shrunk down, so the tires were a little bit flat. But once my car started running, the friction with the ground warms up the tire, which warms up the air inside or nitrogen inside. And so they start to poof back out. So you have to be careful because you don't want to overfill your tires. And then when they get hot because they're running on the pavement, they pop. The odds of them popping, by the way, are really, really small. Like you really have to not really have to overinflate, but you have to inflate them a good bit before you have to be afraid of that. But kinetic energy is the one that you have to deal with in a car crash. The energy is going to go somewhere. So in a car crash, if your car stops moving, all that energy it had when it was moving goes into lots of different things. Okay. I don't know if you guys saw this weekend, but if you did not, let me just show you this quickly. In one of the Grand Prix races, I don't know if you guys saw this. Yes, he was going about 180, 137 is what his, but he would have hit the brakes when he saw he was out of control. So he was going faster than that. This is the car. Okay. And what I want you to see about this is not so much that it's on fire. The fire is a problem. Let me see if I can pull up the video of this because I want to make a point about kinetic energy. Let's go. What am I doing? Yes, he got out of the hospital last night. He has second-degree burns on his hands, but no broken bones. Yeah, it wasn't long. Okay. So
at the UPS store,
Yeah, I
we know
know.
this holiday there's even more you put into shopping.
Thank
We're going
you.
to turn now to the amazing escape from that horrific crash at a Formula One race. The driver, look at that, somehow surviving the.
Okay, so a couple of things about this. They're going to show it in slow-mo. But there's something I want to show you about the crash specifically. So you slow down in the turn and you speed up. Life is good. Oh wait, that's the onboards. I don't want that. I want the get that back. I want his crash. Not the best looks from the. This is the one.
The breakup of his car and then managing
Okay.
to find his way out of those flames.
So
Janae
here's
Owens
him getting
more on
out.
all of this. Good morning, Janae.
Let's slide this over.
Formula One driver.
So here's
Romain
the-
Grosjean is
Here's him
lucky to
going
be
off,
alive,
okay?
escaping this.
Romain Grosjean walked away from one of the most horrifying crashes in recent F1 history at the Bahrain Grand Prix. The harsh driver's car pierced the barrier, split in two, and burst into flames on the opening lap of the race. Yet
That's his
seconds
car,
later,
by the way.
freeing
This is
himself
the
from the
part he
flaming
was
wreckage
in.
and leaping.
Okay. He was in the part of the car that went through the railing. This is where he was. This is the front of his car. A few years back in Formula One history, they had a couple of drivers die. They've had for years Grand Prix drivers die every few years. That's just one of those things. So they had rebuilt the cars about 3 years ago, and they made what's called a halo. The halo, hopefully this video will have it on there, and hopefully we can see it. I'm going to try to pull it out where you can see what I'm talking about.
But
Okay.
based on what we know so far, here are the key factors that prevented a tragedy unfolding
So,
in the Bahrain Grand
He would have
Prix.
died had this been 3 years ago.
How the barrier gave way. The ferocity of the crash was rooted in the speed Grosjean was travelling and the lack of time to decelerate before a sudden impact with the barrier after he collided with
So
the
he had just gotten
AlphaTauri
back
at
into a
Gianni
straightaway, and they
Grosjean
clipped
hit the barrier
right
at an
here.
angle rather than head-on. High-force crashes are not uncommon, but it's rare to see them occur with exposed barriers.
Okay, so here's what I want you to see. They put in this new device called a halo. You see this metal bar that goes around like this? So that's around head height, and it goes around and connects to the back part of the frame of your car, the back of your cockpit, if you will. And in front of it, there's a very sturdy metal pillar that goes straight down between. The reason they put that in was because about 3 years ago, 5 years ago, they had a couple of deaths. And at first they couldn't figure out why the drivers died, because one of the drivers got decapitated and the other driver, they don't know why he died. He was dead, but they don't know why. He's got a crushed skull and they couldn't figure it out. So they start running tests, and here's what they figured out. Cars are way sturdier than humans, which we all know. They made the car to be able to withstand pretty much any speed, high speed, low speed, what everybody's going to say. Car's not going to fall apart. But humans are not so fixed. So here was the problem. The first problem, the reason the guy got decapitated was because he was using straps. It's a 6-point harness. It's like a seatbelt, but it's got 6 places that they connect it. And he was using thinner straps across his chest and shoulders down. So he got chicken winged, is what we call this. His inertia carried him straight forward. The harnesses were too narrow, so it broke both of his collarbones in the impact. And the inertia carried his head forward, and when his body got stopped, his head kept going forward. What killed him was he hit the steering wheel so hard he crushed the steering wheel down, and of course it killed him. The other guy was very similar, except he got decapitated because he left the car. He flew out of the car. So they changed the harnesses, and then they put this halo thing in. The halo is made so that you will hit the halo with your head to prevent you from, yes, it's not, nothing is going to be good if you're in this kind of crash. I get this. But it's to help protect your head from crushing down or snapping due to the forces. So
rather than with the added
there it is right there. You see this? This is called the halo device. They now have it.
protection of TechPro or tyres. While questions have been raised about why the barrier failed in the way it did, it's possible that the sheer force of the crash combined with the angle of the
So
head
he was in that
meant
piece.
that kind of barrier could never stand up to the impact.
And so
Why the car split and caught fire.
more physics.
Once the front end of the car had pierced the barrier, it became trapped. From that moment, to dissipate the energy involved, it was structurally unable to retain the rear of the
The
car.
car broke apart.
With the monocoque containing the driver held in place, the energy led to the rear of the chassis coming away from the driver's survival cell. This part is
That part right there is called the driver's
designed and
survivor
specified
cell,
to firstly protect the
and
driver.
that part
in
was
extreme
perfectly
impacts.
intact, and that's
The
where he
chassis
was
being
in.
trapped in the barrier meant that the energy of the heaviest part of the car, featuring the engine and gearbox, led to the structure around the fuel tank.
This
that
was
is usually
heavier.
part of
The fuel
survival
cell was here,
failing.
and the lighter part of the car is in the
While the fuel
back.
cell is made of Kevlar and rubber and ballistic,
And the fuel cell opened up,
the impact in
and you're
Grosjean's
very
accident
hot,
appears
and
to
the
have been
energy is going to
extreme
go
enough
somewhere.
to
And guess
have
what
damaged it
happens when you
or
get a lot of
torn out
energy
some of
going
the
into
connections
gasoline?
leading to the fire. This structure is part of the survival cell and forms the closed bulkhead
So
behind
there
the
you
driver
go.
that the engine bolts onto. The battery pack was among the debris
There's
that
the
came
battery
away
pack
from the car in the
down here.
impact, and it's a possibility that this very hot component could have played a part in igniting the fuel, something that fortunately we now see very rarely in F1.
Because he didn't hit his head, he wasn't
The
unconscious.
vital role of the halo.
Okay, so I'm gonna skip that part, but he will tell you. I think they have the
Theme of a
images
fire
here.
extinguisher.
Of course,
It was clear
the
Grosjean was shaken,
crash
but
crew
largely
came out as soon as they saw it. Right, they're running with fire extinguishers and everything to put it out.
it
But
could have been a
because
very
he was
different
not
outcome.
unconscious,
There's no question that F1
he was
and
able
the
to get
FIA will
himself
take
out.
this very seriously and learn as much as possible to find
and
ways
he
to
walked
prevent
out of what you
similar
can see. This is
accidents
him
in
jumping
such
over the
unlikely
railing.
circumstances. Fortunately,
He came out of the car right here. This is where he was in the car, and he was able to unstrap himself, jump out, and jump across the barriers just as the extinguishing crew was getting there. So his suit would have been fine. Like his fire suit would have protected him. But the problem is you have places where your fire suit doesn't have lots of layers. And so in the touching of the things to get out of the car, he burned both his hands pretty badly. But he walked away without a single broken bone, which is ridiculous. So when we say there's a lot of energy in those crashes, here's the other thing you need to know about some of this kinetic energy and where does it go. This kinetic energy, what happens if because what happens to our speed right here? What do we do with our speed? It's squared. So if you're going 200 miles an hour, 200 squared is 40,000. This is 40,000 units just from the velocity piece, okay? That energy is going to go somewhere. And in a car crash, a lot of times it goes into us because the cars are perfectly safe. You can make a car as sturdy as you want to. But the human inside may or not be okay. He was very fortunate that there was only about 4 liters of gas left in his tank. They were almost empty on the tank. If it had been the normal 60 kilograms, they probably would have, the heat would have been so much that it would have sort of, not that he would have died because the fire suit would have protected him for a few seconds. But that much heat would be really hard to compensate. So he had some light burning around his ankles and light burning around his hands and on his hands where he was touching things to get out. But he walked out of that without a serious injury, which is ridiculous. So kinetic energy is nothing to be messed with. Now, to go back to our worksheet, which I'm going to do, let's look at some kinetic energy things. Let's look at number 2. Give you a second to read number 2. I'm going to erase this off so I have some space. And let's show what the difference between potential energy and kinetic energy is, just quickly. So in this problem, we are told that we have kinetic energy 1/2 mv squared, and they tell us our toy car is moving with 0.40 joules. And what do we do with our toy car? We're going to do what we did with the glider a minute ago. We're going to double the speed. So as we did last time, where I had V before, oops, you can't see that very well. Nope, 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 not on the ground. Okay, I'm going to put a 2V. I doubled the speed. But what does doubling the speed really do? What would now be in my parentheses? See, the 2 is now inside the parentheses with the velocity. So now what do I really have inside? I have a 4 that I didn't have a minute ago. Here was my original. And now this one has a 4 that I didn't have a minute ago. So now I have to put a 4 on that side to balance it out. So this one is also 1.60 joules. Because the speed is getting squared, whatever you do to the speed, you have to square that number. So if Brian was to square 3, he tripled his speed. If he triples his speed, he actually has 9 times as much energy. If he halves his speed, he has 1/4 as much energy. So the most important thing that you can ever do in a car accident, if you have the opportunity to do something at all, is take as much speed off your vehicle as possible. Because the more speed you have, the more energy you have, and that energy is going to go someplace. So if you can hit the brakes and take some speed off your vehicle, do it. Most of the time in a wreck, you don't see the thing that hits you. And sometimes you can't do anything about it because you're in the middle of traffic and the person behind you hits you and you hit the person in front. Or the person changing lanes hits you and you don't see them on the side. So you can't always do that. But when in doubt, make sure you slow down. Slow down in a crash will take a lot of energy out and it'll make a huge difference. Okay, so let's do one more like this. Calculate. Let's do this one down here. That's number, let's do number 8. Calculate the speed. So we're going to be looking for speed. So kinetic energy. And yes, I do write the formula every time. I know these formulas by heart, but I still write it down. Kinetic energy, they tell me it has 26.1 joules of kinetic energy. They tell me my mass is 5.2, and I don't know the velocity. So what is the first thing we should do here?
Can you scoot it over?
Yes, I can, sorry. Is that better?
Thank you.
Yes, you're welcome. I'm sorry. Sometimes I don't realize that.
Well, you have to get the velocity to be by itself. So you would divide 1/2 on both sides and 5.2 on both sides.
Mm-hmm.
And that would give you your velocity.
Right. So you can do one of two things. You can either divide both sides by 1/2 and 5.2. I like to do these where I go ahead and simplify that. So I would do 1/2 times 5.2 and get 2.6 v squared. And then that way I just divide by one number instead of two. That's a personal preference. So v squared equals 10.03, I think. So what I got? (26.1) divided by 2.6. 10.04 actually. Now what do I do once I've got v squared by itself? How do I undo squared?
Well, you take the square root of both sides. So
Okay.
take the square root of 10.04 and v squared.
So I would take the square root of this side and the square root of this side, and I would get v equals 3.2,
3.17.
3.17. So I'm going to round that off to 3.2 meters per second because it is a speed. So I'll wait here for just a second. You've got some other problems like this, like number 6 is like this. Not exactly the same, but it's still a kinetic energy problem.
Did you say 3.2 meters per second squared or 3.2 meters?
No, it's
per
meters
second?
per second because it's velocity. Yeah.
Yeah. Okay.
Okay. All good. All right. So then you have that worksheet. This needs to be finished by Friday. How did I say you do total mechanical energy? How do you do total mechanical energy?
You compare the kinetic and the potential energies.
Good thought. Not quite right.
So
What does it mean to total something?
you can either add them, subtract them.
So to total something, like if I was to total my bill at a restaurant, I would be adding things up, right? So total mechanical energy is kinetic energy plus potential energy. So for example, at position B, what is our total energy? 5,000 plus 4,000 is
9,000.
9,000 joules. Total energy is just all the energies added together. So that one's the pretty easy part. Now let's go over here. I'm going to look at the other one with you real quick. I'm just leave that. Thank you. Still sharing my screen. Share my screen. Got that going. So the other worksheet, if you go to Teams, and I'll just start doing this because it seems like y'all can get to this part really easy. The notebook has been sort of a hot mess all semester. So if you just go to your Teams, I'll post in this front page your assignment. So here's the energy concepts. This one is 3 pages front and back. Okay, so it's kind of long. And you don't have to do all of these right now. We're going to do some of these as we go on, but you can do some of them. Like you could figure out the ranking. Which one of these points has the most potential energy? In this picture right here, which is the, let's see, energy concepts 1, 2, 3rd page. It says to rank in terms of increasing potential energy. So where do you have the most potential energy? What location?
A.
The highest point is going to be your most potential energy. Who's going to be next?
C.
And then?
D, then E, then B.
So we just go down the hill, right?
Right.
And B is the smallest because it's the lowest point. Then they're going to ask you when you're going fastest. That's another piece they're going to ask. So that's kind of how those go. So feel free to do as many of these as you can, but we will talk about the bar charts and the other calculations starting on Friday. So the only thing that you have to turn in is the energy worksheet, which is the first one down here. And then beyond that, you're welcome to stay or go as you need to. It's good to see all you guys. Take care. And I'll hang out here in case you have some questions. And if not, have a wonderful, wonderful day. The only thing I don't have graded is your labs. And I will hopefully have all the rest of those graded tonight. I got two of them graded. I got 3 more to do. Thanks. You guys have a great day. I appreciate it. Thank you for the kind notes. Appreciate it. And I will see you on Friday. And then we'll just have 2 weeks of school left.
So on
Yay.
number 2, is
Yeah.
kinetic energy tripled?
Yes. So since kinetic energy depends on velocity squared, if you triple the velocity, what is the square of 3? What is 3 squared?
9.
So you would have 9 times as much kinetic energy.
Okay.
Does that make sense?
Yeah.
Okay. All right. I'll just be hanging out here. I'm going to turn this off. Today's Wednesday. I don't have any meetings after school today. Yay. No meetings after school.
You said that the velocity is 3, and you said that if you triple it, it's
If
9.
you triple the speed,
Wouldn't you have 3 times as much kinetic energy?
nope, you would have 9 times as much because the tripling of the speed is inside the square.
Okay.
So
Guess
since it's inside the squared, velocity gets squared. If you triple the velocity, then you've got 3v quantity squared.
Okay. I think I get what you're saying.
I'll write it up real quick. Let's see. Put that whiteboard back up real quick. So if we put in here 3 times the velocity and square it, then we get a 9 that wasn't there a minute ago
Right.
when we simplify it. So the energy would be 9 times as much as before. This is the old. This would be the new.
Okay.
Okay.